Hello, and welcome to the continuing journey of Worksheet 8. My candle is still burning and it smells like pine in here, which is always a good thing. Anyways, the next part of this worksheet is going to be on KD trees. So KD trees are a rather esoteric but nifty data structure in that they allow you to partition an arbitrarily dimensional space into a bunch of regions which you can then search. So in other versions of this class, we have a project in which you have to implement these and do a lot more with them. In this version of the class, we're going to be hitting them pretty lightly. So if you start doing past midterms and you notice that the KD tree problems are like way harder than they are this semester, it's because we don't always teach them in the same amount of depth. This time it's going to be really shallow. Sometimes we don't teach them at all. But basically, don't worry too much about it. This itself is a rather surface level KD tree problem. We're not going to be doing the nearest algorithm or anything. We're basically just going to be partitioning some space and getting a feel for how we would partition space with a KD tree. Okay, so this question is giving us some points on an XY grid. So this is a KD tree, but really it's a 2D tree. Oh, that's, get it, the question, it's question 2. Anyways, we're just going to be partitioning this. And we want to create the corresponding KD tree. It'll partition all of this information. And we want to make it perfectly balanced. Why did they say perfectly balanced? I don't really know why they use that terminology. What they mean is they want it to be bushy, right? Notice there are 7 different points on this 2D plane, and we are going to want a tree that looks like this, meaning there are 7 points. It's just a bushy full tree. That's what I mean by perfectly balanced. Okay, final rule is we're going to be splitting on the X dimension. Resulting tree should be complete with height 2, which is what I just drew on the right. Okay, and then draw the corresponding splitting planes on the grid. Okay, so how does a KD tree work? We're just going to talk about it really briefly again. So normally in like a BST or something, you have nodes that each have one element. A KD tree is different because it's going to have K elements in each node, each element representing a coordinate. Again, this is a 2D tree, so we're going to have 2 elements per node. So if you have, for example, the node 5, 2, basically what this means is that this represents a point 5, 2. There's one point right here corresponding to that. And then we are going to split these dimensionally. So everything to the left of 5 is going to have an X value of less than 5, and everything to the right is going to have an X value of greater than 5. Why the X value? Because we can't compare on both values at the same time, right? That wouldn't work. So we just have to pick one arbitrarily and then we alternate. So you might end up with something like 1, 6 over here. And then the left child of 1 is going to be everything that is less than 6. And the right child is going to be everything that is greater than 6, right? We're going to basically split on the x-axis, then judge based on the y-axis, x-axis, y-axis, alternating. This is a 2D tree. If you had a 3D tree, it would be x, y, z, x, y, z. You'd just alternate every 3, but we're only doing it with the 2. Okay, that's a little bit of how they work. I recommend you familiarize yourself with the lecture again if that didn't make sense. Now we're actually going to do this problem. So we want to split this space to be perfectly balanced. Okay, how do we make the tree perfectly balanced? Well, the tree is perfectly balanced when we have the same number of nodes on one side as we do the other side, right? Keep in mind in this example here, we have 7 nodes. There's 1 node at the root, and then there's 3 nodes to the right of the root, and there's 3 nodes to the left of the root. Correspondingly, that means that basically we want to start with a point that we can then split the remaining space into 2 sets of nodes that are equally sized. Okay. We know that we are starting the split on the X dimension, so we want to draw a vertical line, because that's how you split the X dimension, such that it will have 3 things on one side and 3 things on the other side. And I can see how we're going to do that. We're going to do it down this line, because we have a point 5, 2. And if we split down 5, 2, we have 3 on the left, and we have 3 on the right. So that means the first node that we are going to want to place into our tree will be 5, 2, like this. I did it earlier subconsciously, but it's 5, 2. Okay. What is that going to mean for our actual graph representation? It means we're going to end up with something like this. Right? Remember, 5, 2 has 2 children. Everything to the left is going to be less than 5 on the x-axis, and everything to the right is going to be more than 5 on the x-axis. And you can see that correspondingly here. Any point here is going to correspond to the left. Any point here is going to be on the right. Okay, so next we're going to split on the y dimension, and we want this tree to be perfectly balanced. So notice in the same way that we said, okay, we want to have 3 and 3 on this side. When we go down to the next node, we're going to have 1 and 1 on the next side. In other words, we've just split this 2D grid into 2 sections, each of which contains 3 elements. And now we're going to split each of those 3 element sections into 2 more sections, each of which contains 1 element, right? And we're going to split it along the y-axis. So if you look here, you can try to figure out which remaining points we can use that we're going to split on the y-axis. Okay, so let's look at 2, 7 first. 2, 7 and 8, 2 are the ones we're going to do. It doesn't matter what order you put them in because one's on the left side, one's on the right side. They're not going to interfere with each other. But let's just do 2, 7 first. So if we want to put 2, 7 into our tree, we can just put it here. Remember, it goes to the left because we are comparing things based off the x coordinate at the first layer up here. It's going to have a left child and right child. The left child is going to represent everything less than 7 and everything greater than 7 up, right? And what does the corresponding diagram look like? You'll often see it drawn in blue. It is going to look like this, basically extending out infinitely in that direction. Okay, why does it look like this? Why doesn't it look like this? Because remember, everything that goes to the right, or to the left, sorry, of this first node has an x coordinate that is less than 5. And we see right here is the point where if we were to continue going, our x coordinate would get greater than 5. That's why we're going to not go past that line, right? Another way to think of it is we split, when we drew the red line, we split this into 2 sections, this section and this section, and now we can only further subdivide those sections. We can't cross over sections anymore. Okay, so let's do a corresponding action on the right side. On the right side, we're going to put the 8, 2 node in like this. And that means we are going to split this on the y-axis, just like this, and just for all the same reasons that we can't go beyond in this direction, for all the same reasons that we can't go this direction with the first one we drew, we can't go the other direction, right? Okay, so now we are at this point where we have 3 nodes. Now we just need to add in our final nodes as leaf nodes, and then we are done with this problem. Okay, so you don't have a lot of choice of where to put the last nodes in. For example, if we look at 1, 8, there's only one place on this tree that 1, 8 can go now, because 1, 8, if we sort it, first we're going to compare 1 to 5, so it has to go to the left. Then we're going to compare 8 to 7, so it has to go to the right. So it has to end up here. So if I just draw it there, 1, 8, it's going to look like that. And then we are going to have our corresponding line up here. Look how straight that line is. That was a pretty good one. Just going up like this, right? It's subdividing this space and this space. Okay, and the rest of them are going to be very, very similar. So let's say that we put 4, 5 in. 4, 5 is going to end up going here. Let's say that we put 7, 1 in, going to end up here. And let's say that we put 9, 5 in, going to end up here. What are the corresponding lines going to look like for all of them? Well, 4, 5 is dividing this quadrant on the x-axis, so it's going to look like that. 7, 1 is dividing this quadrant on the x-axis, it'll look like that. Then 9, 5 is dividing this quadrant on the x-axis, so it will look like this. So you end up with a very style looking kind of fractalized view of the world. And that is basically how you would draw a KD tree, such as evenly balanced. You would split things up equally each time. And that is all you have to do for this problem.